Hello, am I audible?
Yeah, you are audible.
Yeah, okay. So right now, which I have actually slowly uploading some of the pending session because I couldn't take it because of some other assignment. I already informed the NPTEL team, but you will find this thing slowly in the YouTube channel. So currently,
Okay.
what topic sir is covering, like optoelectronic devices and solar cell, or mainly the IC and op-amp related stuff?
Now, what is the thing happened means for me past only 1 or 2 sessions only I was able to attend. I was facing problem with this entry. I sent message to the team after that. This week only I was able to enter this
Okay.
teams.
Okay, no
Uh,
problem. It's not an issue. You'll find all the videos on the YouTube only. Are you able to see all these videos that I have uploaded?
uh, Second or third week video I have seen. After that, in between, I couldn't find time to see the video.
Okay, okay, no problem. I just wanted to ask because recently not much people are joining the classes, so it's fine. I mean, I
Okay.
just wanted to have some update on this, but it's
Maybe
okay. So,
problem with that entry, I think. I was waiting in the lobby for a long time. Nearly half an hour I used to wait. I am not able to enter.
no,
Then I
actually,
left.
last two classes I couldn't take, so I already accordingly made some of the recorded videos for this because
Oh,
I
okay, okay.
available for last two classes. But other than that, all the classes I have taken so far. So
Okay,
you will
okay.
okay,
I
but
have
maybe
attended only 1 or 2 sessions only. After that, none of the class I was able to enter. So after
okay.
that, I wrote a mail and today I was able to enter.
Yeah, it's fine. I think there are some other problem because you will see in the YouTube session a lot of people
Mm-hmm.
already attended in like
Okay,
till
okay.
weeks seven. Yeah, so it's fine. So I will accordingly. Today I have planned to show you some of the problems related to integrated circuit and op amps, and I will
Okay.
also cover some problems from optoelectronics. So that's what I can see based on the week 10 he has covered. So, I mean,
Okay.
optoelectronics problems are pretty much simple, but there are some problems I wanted to discuss. Also, students have mentioned some
Okay.
difficult problem from IC, so that I will discuss. You can just see them. Yeah.
Okay. Okay. Fine.
So, yeah, I'm sharing my screen. Just let me know if you are able to see. Can you see?
Ah, yeah, I can see.
Okay, fine. So, problem one is, yeah, I will first write it some of the key terms. Consider the inverting op amp of a figure that I will show below with R1 10 kilo ohm, R2 50 kilo ohm, and power supply voltage is plus minus 12 volt. So you have to find out the output voltage and input current for an input voltage. Sorry. Guys, please unmute yourself. Also find the output voltage for the input of 3 volt. Okay. So I'll draw the schematic now. Let me just quickly say 10.9.1. This is the inverting op amp. So for problem first part of the problem, the output voltage already will use the expression. The output voltage which I derived earlier. Vs R2 R1 is already given. It's 50 kilo ohm divided by 10 times 0.5 volt, which is minus 2.5 input current. Now if we put Vs equals to 3 volt, so V0 will comes out to be minus 15 volt. But in practice, the op amp does not remain in this case within the linear region. The op amp saturates and output voltage leads to minus 12 volt. So that's why important one, which is the supply voltage. First I will draw a schematic in point 10.1. Oh, another one I just forgot to mention in the last class about the logarithmic amplifier. This is an important one. Generally, for typically competitive exam, you might expect this kind of thing. So this is first I'll draw the schematic. Sorry, just have to. This is your output with respect to a ground. This is the source voltage, but it can be variable. Okay, so this is your source current. Well, these directions are very important, so please follow these notations. And the diode is placed here. So, and now I'll tell you why this is called this kind of circuit calls as a logarithmic amplifier, because already you are using a uh, diode in this case. So here the circuit diagram of the logarithmic amplifier I have highlighted, whose output you will see this proportional to the logarithm of the input voltage. So here the is equals to IF, right? Here the resistance, the input impedance between these two is infinite. That's why the current always go through this direction. It will not enter here. So technically, I is equals to IF, or you can write PS just for a closed loop circuit. You can write this is your sorry. This the resistance is R. I forgot to mention. So this is Vs minus 0, because this point voltage we always consider it to be 0. Yeah. So that is equals to IF, or we can write Vs by R equals to I naught. It is the forward bias diode current. Okay, that I have mentioned in maybe first or second class in this for this course long back. What will be the condition of the forward bias or diode in this case? So VF is the forward bias voltage. Technically, this term is very like this term is bigger compared to one. So you can just simply, for the sake of simplicity, you can approximate it to exponential e to the electronic charge EVF divided by eta kT. So eta will depend like whether you are using a silicon or germanium based semiconductor as a diode, and finally, the output is an inverting op amp. So V naught equals to minus Vf, which is eta over kT by E ln of Vs by I naught R. So here I naught is basically your reverse saturation current. I hope you guys are familiar with it. Reverse saturation current, and eta equals to 1 for, as I was mentioning, for germanium, and eta equals to 2 for silicon made diode. Sometimes you can see these options will not be given in the question, so you have to remember this parameter ka value for both the cases of silicon and the germanium. So that is why it's called the logarithmic amplifier. So I'll also discuss the, before showing you the some of the problems, I will show you the differential amplifier ka some of the terms that will be important in this context. The differential amplifier. Let's say you have V1 and V2 are the input signals applied to the non-inverting and the inverting terminals respectively. Then your output voltage of an ideal op amp will be AD times V1 minus V2. Okay. AD is basically gain for the difference signal, which is V1 minus V2. So in case if V1 equals to V2, then differential amplifier doesn't work. It will give you output of 0. Okay, but in practice generally this is not the case, because output will not only depend on the difference signal, it will also depend upon the, so in practice this is important. So in practice, start once. on the average level, which is defined as VC. You just take the average of these two input signal. It's called the common mode signal. This is very important. So you will expect a lot of problem related to this topic in any kind of competitive exam as well, which is called the common mode signal. Sorry. So thus in general, V0 equals to AD plus AC VC. This will be the total complete output in this case. And your AC is the voltage gain, or the common mode signal. So in ideal case, it equals to infinity, is equals to 0. But in practice, this is not true. That's what I just mentioned. So basically, to express how successful this differential amplifier is in providing the gain of the difference mode signal and rejecting the common mode signal, we generally introduce a factor which is called, maybe let me change the color of it. It's called, sorry, it's called common mode rejection ratio. Also in short, we call it as CMRR, which is defined as the ratio of the two different gains that I just highlighted above. And take the mod. It serves generally as a figure of merit for a differential amplifier. Differential amplifier. Sometimes also expressed in decibel. This is very important in electronics. Actually, some of the cases you'll find it is expressed in decibel. Then you have to quickly change it in this form. Take log 20 of log 10, then this AD by AC. You will simply might be asked to write in the decibel form. Then you have to take this expression in order to get the gain CMR. Next is there is something called, I'll discuss about phase shifter. So I already shown this figure of this invert, sorry, not this one, the inverted amplifier, this one. Remember this thing. So the same figure I'll be using to explain this for the inverting amplifier. You assume the resistances R1 and R2, which are the input resistances, now getting replaced It's a one of the, like, you might ask in a different manner in any kind of question. So instead of simple resistance, the you will be given with some impedances. Let's say impedances of Z1 and Z2 in this two arm. Okay. Then therefore your gain will be, this thing will be simply Z2 by Z1. Okay. Now if Z1, if Z1 and Z2 are chosen to have equal magnitude, but different phase, then what you can write from here? We'll simply write, so I'll take the magnitude and the phase, which is, it's a complex number, right? So there will be a phase associated with this. Let's define it as phi 1 and phi 2. So we'll simply get e to the power j pi plus phi 2 minus phi 1, because minus you can simply write I pi, oh, sorry, j pi. Yeah. So this is the difference in the angle. Okay. Okay, summation difference amplifier I have told.
कोविड में हालत खराब हो गया मेरा, उल्टा बेइज्जती।
Yeah, so yeah, sorry for this because this guy is continuously unmuting himself and just disturbing to the entire class. Sorry for that.
No issues.
Yeah, so there is something called voltage comparator also. I don't know whether all these things were also discussed, but these are uh, sorry. Just voltage comparator. So first I'll draw the circuit. Yeah, so this which you can see, we can compare two voltages here. It's also an op amp, which basically compares the input signal Vs with a reference of voltage Vr. So this is your input signal, and with respect to Vr, we are comparing this thing. So as long as your Vs is less than Vr, the output voltage V0 goes to maximum positive. Yeah, so V0 goes to the maximum positive saturation value as Vs crosses Vr. So where basically your Vs becomes greater than Vr, the op amp in that case, your op amp output switches to value of negative saturation maximum, which is we can define as minus V sat. So thus by looking at the output voltage, we can instantly identify whether the voltage like Vs is greater than or less than. So this is what we use as a comparator. So let's say you are giving a signal trend. So if I'm drawing a sine curve, it's a sinusoidal signal, which is my Vs. Sorry. So for your simplicity, I'm giving a reference voltage of 0. Okay. So if I want you to tell me the corresponding output voltage, so this is with respect to time. Okay, so if my reference voltage is 0, then you can expect, right? This is an inverting amplifier. So for the first positive half, so it will give me a negative of maximum minus V saturation. The moment it crosses 0, sorry, Yeah, the moment it crosses 0, it will hit to plus. Rather, I can do one thing. So something like this. It's a full cycle. So this will be your complete output. Something like this. Okay. This is 5, this is 6 now. There is something called Smith trigger. Or regenerative comparator. So the simple circuit for the Smith trigger is like something like this. Again, the same thing, but with a slight modification in the input resistance arm. This is your reference voltage. The resistance we're defining as R1. This we are defining as R2. At this point, we're defining as V1, and this is your Vi or Vs, whatever you defined. So as I already mentioned, when Vi is less than V1, the output is at positive saturation level plus Vset, and then so basically your V1 will be R2 VR divided by, it's simple, I mean it's in the, it's the resistance drop plus R1 Vsat. Basically it's a superposition principle, and then let's say you are getting V1. Now let's say if Vi is now increased, and then basically the output remains constant at Vset, and V1 equals to capital V1 constant until, so basically your V1s will be capital V1 and it will be constant until you are getting V1, because it's a comparator circuit. V1 equals to capital Vi, sorry, Vi equals to capital V1. So at this threshold, basically it's a critical point, right? So the output regeneratively switches from like whenever it will try to do that, the moment it crosses it, so V0 will immediately switches to minus Vsat, as I already mentioned. Okay. So then what will happen in the case of, let's say, Vi greater than V1? It's simple actually. So it will define as V1 will change. This first term will remain the same, R1 plus R2, but the second term will be changed because it is hitting to minus Vsat now. So R1 minus Vsat, like already I kept the minus here, and R1 plus R2. Okay, let's say this is my V2, say. So something, some sort of characteristic picture we can draw here. Basically, what will happen with the increasing Vi? This for V2, and this is minus Vsat. Okay. Six. Now I'll come to 7. This is a problem. So suppose a sinusoidal signal Vs equals to 10 sine of 2000 pi t, unit is millivolt, is applied input of the op-amp integrator of a figure that I will show below, with R is already given of 1 mega ohm, and capacitance is also given 1 microfarad. So you have to find out the output voltage for this. Okay, so now I'll show you the schematic. ST10.5. This is the integrator circuit. This is the capacitor. This is the resistance or resistance R, and this is your Vs input signal, and V naught is the output. Okay. So it's integrator circuit. So we'll know the what will be the output 1 by RC and 0 to T. This is VST. Okay. RNC will plug it in the final in the last line, but now we'll focus on the integration. So it's a sinusoidal signal. Okay. So we solve this, you will get. You can also check by yourselves. You cross check all the like numericals. That's always recommended, because I'll be skipping some of the steps for the sake of time. It's still in millivolt. Time is not defined here, so we'll leave as it is with the most simplified form that we can do, something like this. Okay. So moving to the next one, the input to the op amp integrator of the same above figure, the same one. Let me just go to the next line. Of the I just shown is a DC of 1 volt. Find the nature of output voltage. Now assume R equals to 1 mega ohm, C equals to 1 microfarad. Similarly, we'll use the same expression. You'll get something like, if you solve this, because it is of 1 volt, so you will get minus T volt. Now as the output is a linearly decreasing ramp voltage. In just 1 second. So I'll also draw this thing. It's a very understandable one. It's 45 dB kind of thing. So it's time, and this is your output voltage. This is -1 volt. This is 1 second, and this is your ramp. Next problem. Ramp voltage of 1.5 volt per millisecond. Figure I will show below is applied to an op amp differentiator. So I already, integrator I have shown you. Now I'll come to the differentiator portion with R equals to 2 kilo ohm and with the given capacitance of 0.01 microfarad. So to basically find out the output, find out the output voltage and what will be its waveform, how it will look like in time basically. This is the input. So the same current will follow this path, and this is how it looks like. It's a differentiator. So as per the questions, This is the ramp voltage to 1.5 volt per millisecond. So this duration is 1 millisecond, which is given, and it is ramping from 0 to 1.5 volt. Now from this figure, and this is 0 outside the 1 millisecond range, because the difference is 0. We are not ramping anymore outside this particular 1 millisecond time window. Now the output will become if we simplify, we'll get 0.03, which is minus 30 millivolt within 1 millisecond range. So now how the output will look like? It will look like this. This is 0 volt reference line, and time window is 1 millisecond minus 30 millivolt. Okay, this is the output waveform. Now I'll come to problem number 10. Just 2 minutes, guys. I'll be back. 3 minutes. Yeah, so problem number 10 is what is the output voltage in the circuit of that I will draw below. Explain the operation. The operation. Let me draw the circuit first. This is a diode and this is a capacitor. So there are some conditions that we have to incorporate here. Only then we'll be able to solve this. So if the V is the input voltage greater than V naught, the op-amp output V prime, let's say this is V prime, is positive, the diode D then conducts, because it has to be in the forward bias, right? Only then it can conduct. And eventually the capacitor also will be charged up. C is charged to the value of input, because the gain is unit, right? For this circuit you can already see there is the R1 and R2 you can simply consider it's same. I mean there is no resistance is connected, so it's a gain unity circuit. So gain of the circuit unity. So in this way capacitor is charged to the peak value of the output, which is V naught. Oh, sorry, peak value of the input, not output. when Vs goes to below the capacitor voltage, op amp output, let's say V prime, becomes negative. This becomes negative. Now then the diode becomes reverse bias, right? It becomes reverse biased, and it will not conduct. However, the capacitor voltage remains at the peak value of V naught of the input. So this does the circuit acts as a peak detector. This was the peak detector circuit, and this was the conditions when it will be operational or not. Okay. Now consider next problem. Amplifier of figure that I will show with R1 equals to 1 kilo ohm, R2 equals to 50 kilo ohm, op amp supply voltages is plus minus 12. This is a very common, I mean, plus minus 12 is always you will find is the operational condition in most of the op amp. To compute the gain and find the output, if input is 0.5 sine 100 pi t in volt. Okay, so yeah, circuit I have to draw. is the actually same circuit. It's the inverting op amp, which I shown at the very beginning. This one. So maybe let's refer this as a figure one, so that later point of time I need, I'll just recall as figure one. This is the elementary figure for this kind of inverting op amp. So the gain of the amplifier is basically, it's an inverting one, so it's a negative gain, minus R2 by R1. So it's basically minus 50 by 1, so it will give me minus 50. If the op amp were within linear region over the whole range, then the output would have been V naught minus 50 Vs, which is minus 25 times sine of, which is already given, 100 by T, right? Since the supply voltage, that is why this logic is important here, I'll show you. Is the supply voltages are plus minus 12 volt, the output saturates at plus minus 12 volt only, right? Yeah. The output will be sinusoidal voltage anyway, sinusoidal voltage of minus 2500 pi t volt with sharp clipping, that I will show in the diagram. Clippings at plus minus 12 volt, right? So that is why this problem is important. What will be the realistic one? So if I draw this accordingly, output voltage, you will see the time, maybe you can consider in second, and this is the output voltage in volt. Okay, and let's say this is my plus minus 12 of this op amp voltage. So from here it is fine, but the moment it will try to go beyond this, it will be cut off. So that's why this clipping will be there. So till this point it will saturate to minus 12 itself, and then there will be again a clipping at plus 12. Okay, right? So this is how it will be. So this region is, sorry, this is forbidden. Only till this it will occur. Yeah, now the next problem. Okay. Problem number 11. Now coming to problem number 12. One sec. Consider the circuit of figure I will show below. Now find the value of R3 which minimizes the effects offset current. Assume the output impedance is 0. I mean, which generally so far we have assumed this only. So now I'll draw the circuit. This one, and this is your R3 that you have to calculate. This is 2, this V0. Okay, fine. Now the DC output impedance of the op amp is low, and the output terminal effectively at ground for DC. the current I1 passes through this resistors R1 and R2, but in parallel, because this is your I1 and this is your I2. Okay, hence the potential at point 1 is V1, which is simple. I mean, it's in the parallel combination, right? So, but it's inverting op amp, that's why there is a minus sign. Yeah. Now at the potential I2 R3, right? So hence the output voltage of the amplifier is given by V2 minus V1. Thus V0 is 0 only if we choose R1 R2 plus equals to I2 R3, only then it will become 0, right? So therefore R3 is I1 by I2 Now, if your I1 is almost equals to I2, then R3 becomes R1 R2 divided by R1 plus R2. Remember this one. So yeah, I mean R3 has no effect on the virtual ground approximation because the no AC signal current flows through it. So that is the reason. Now moving to the next one. This is problem number 12. Now problem number 13. Let me draw the circuit first for this case. This is the op amp, plus minus is your output. Vs. This is V2. This point potential is V1, and the total output is defined as V0. The resistance value is given is NR, and this is R. This is Vs. Done. So here in the problem it is mentioned that to consider the differential input amplifier of this figure. Now assume infinite input resistance. We generally so far in this context we have assumed that, and zero output impedance. So that's the ideal condition for the op amp. So if it is not mentioned in the problem, you guys can also assume that like explicitly. Yeah. So and zero output resistance. Finite differential gain, which is AV equals to V0 divided by V1 minus V2. Show that the closed loop gain is given by AV plus AV divided by N plus 1. And also it is mentioned that discuss the case of like where AV is tends to 0. So now the solution part. V2 is V naught R divided by NR, because that is one of the resistance of the arm. And so if I take R out in common, so it will give me something V naught divided by N plus 1, and your V1 is S. So V0 is, if it's a differential amplifier, so V1 minus V2. So AV is Vs minus V naught divided by N plus 1, or maybe just one second, or the AVF Vs, because ultimately we need in terms of V naught and Vs. Only then you can find out the closed loop gain. So if you do the simplification, you will get AV divided by AV uh, n plus 1. Now in the limit AV tends to infinity, we get AVF of n plus 1. Done. I'll do one last problem from the common mode rejection ratio, which I just uh, today explained you if, in the initial portion of the class. So yeah, problem number, I think it will be 14. In a differential amplifier, differential means always it will have two input with two inputs. The output is, it is already given, which they're saying is close to, sorry, that's millivolt when the inputs are 110 microvolt and 90 microvolt as per the questions, but so output is 2 millivolt when corresponding inputs are 10 microvolt and minus 10 microvolt respectively. So in this condition you have to find the common mode rejection ratio, which is CMRR of the amplifier. Okay, so you know already I have told you. So the expression of V naught, in this case the final output, is this, right? Now in the second case, Vd equals to 20 microvolt and Vc equals to 0, the average one. So write 2 millivolt equals to AD times 20 microvolt. So my AD is 100, right? And in the first case, 0.01 millivolt. So 80 already we have obtained. This is 20 microvolt times AC 100 microvolt. This is this. So CMRR is the ratio of this AD and AC. AD is 100 and this is 1/10. So you get a CMRR of 1000. Maybe I'll just show one more problem. Yeah, just problem number 15. So first I'll draw the circuit. So this is your R1. This is R2. This is R3. This is R4. This is V1. This is the output voltage V0. This point is A. This is V2. Okay. Yeah, so you have to prove that in this problem your output voltage in this case will be R1 plus R2, R3, R4 minus V1. It's actually simple, but it appears to be difficult. But yeah, you have to just do it systematically. So again, you have to find out the V naught by superposition principle. Okay, this like this you have to use most of the time in the case of whatever problem you are going to solve from op-amp. This is very important. That is why I'm explicitly writing superposition principle. There is some lag in my iPad. I think that's why the superposition principle. V01, that is R2 divided by R1 V1. Okay. Output voltage due to, let's say, V1 alone. V1 alone. Okay, this is V01. Just assuming. Okay, and then voltage at non-inverting terminal is VA is equals to V2R4 R3 R4. Therefore, output voltage due to V2 alone now is, we can define as V02. So this is how you have to take the approach for solving this kind of problem. You just consider the individual uh, contribution and then sum it up. So this will be V2 R1 plus R2 and R3 plus R4 R4 by R1. Hence, by superposition principle, the resultant sorry, the resultant output voltage V naught is to V01 plus V02, right? So is V2. If you simplify, you will see that you will get exactly this R3 R4 and V1 R2 R1. Done. So I'll stop here today. So it will be uploaded also in the YouTube. And if you guys have any other questions, you can also anytime write me in the chat section of the Teams, or you can also send any of the questions to my account. I will be discussing in the next session if any pending questions are there. Okay.
Thank you. Yeah.
Okay, no problem. Bye. I'll stop here and you guys can exit here.
Okay. Thank you. Bye.